This podcast was created as a supplemental learning resource for this course. The content is based on assigned course materials, including open educational resources, textbook chapters, instructor-developed explanations, examples, and applications connected to course topics. AI tools were used to help transform course material into a conversational podcast format, including the use of AI-generated narration. The AI narration is intended to make the material more engaging, accessible, and flexible for students. However, the podcast should not replace careful reading of assigned materials, reviewing course lectures, or completing course activities. Any interpretations, examples, or explanations included in the podcast are provided for educational purposes and are the responsibility of the instructor. Students should rely on the assigned readings, course lectures, and official course materials as the primary sources for exams, assignments, and class discussions.
So, the mathematical formula that you basically rely on to pass your entire psychology degree, it was actually invented to protect the recipe of Guinness beer.
It is honestly like one of the greatest and probably most unexpected origin stories in all of modern science.
Right. Okay, so let's unpack this right away.
Yeah.
Because if you are listening to this deep dive right now and you are, staring down a massive mountain of statistical concepts.
We're trying to figure out t-tests and p-values and all that.
Exactly. You might be feeling incredibly intimidated. You might be thinking, I am not a math person. I am a people person. I want to study psychology, not crunch numbers in some vacuum.
Totally understandable. It's a very common feeling.
But we are going to completely demystify this today. Our mission for this deep dive into the source material is to understand exactly what t-tests are, when you use them, and how they actually connect to real human behavior.
Yeah, and to do that, we kind of have to travel back to a brewery in Dublin, Ireland in the early 1900s.
Oh, I love this story. So paint the picture for us.
Right. So picture the Guinness Brewery around, let's say, 1899. At this time, they are really industrializing their brewing process. They aren't just making small artisanal batches anymore.
They're brewing on a massive, global scale.
Exactly. But they have this incredibly strict goal. Every single pint poured anywhere in the world needs to taste exactly the same.
It has to be 5-star quality every time.
Right. So to guarantee this, they actually hired brilliant chemists and scientists, and one of them was a man named William Seeley Gossett.
Okay, so Gossett's job is basically just to make sure the beer is perfect. Which sounds like an amazing job, honestly.
Not a bad gig at all.
But he runs into this massive logistical nightmare, right? Because they would brew these giant vats of beer, and they needed to test the extract, the acidity, the overall quality.
Yeah, and to absolutely guarantee that the entire population of that specific vat was perfect, they would theoretically need to test every single drop.
Which is obviously impossible.
Right, it's called destructive testing. If you test the whole population of the vat, well, you've consumed the entire vat.
There's absolutely nothing left to bottle and sell.
Exactly. So he obviously can't test the whole population. He can only pull a small sample, maybe just a few cups.
But this is where the panic sets in, right? Because if you pull a small sample, how do you know that sample actually represents the giant vat?
You don't. Not inherently.
Because what if you just happen to scoop out a weirdly bitter part of the batch purely by chance?
And that right there is the exact same fundamental dilemma that behavioral scientists face today. It is literally the absolute core of all psychological research.
Oh, wow. Because we want to know a universal truth about an entire population.
Precisely. We want to know how all infants learn, or how all adults experience anxiety, or, how human memory works globally.
But we can't possibly measure every single human being on Earth.
No, we can only ever look at a small sample, like 30 college students in a lab, or maybe 50 infants in a clinic.
So Gossett basically needed a mathematical way to look at a tiny sample of beer and calculate exactly how confident he could be that the whole vat was good.
Yes. He had to mathematically quantify trust. And to do that, he invented what we now know as the t-test.
He actually invented it for the beer. That's incredible.
He did. And what's really funny is that Guinness considered his statistical method to be such a valuable trade secret that they wouldn't even let him publish his paper under his real name.
Wait, really? They made him hide his identity?
Yeah. So he published it in an academic journal under the pseudonym Student.
Oh, Student's t-test.
Exactly. That is why, to this very day, it is officially called Student's t-test.
Yeah.
It wasn't invented by some stuffy academic in a tweed jacket disconnected from reality.
It was invented by a guy trying to solve a real-world, high-stakes quality control problem.
Exactly.
I love that so much. It really reframes the whole concept for you. Statistics isn't just arbitrary math. It is a way of reasoning with uncertainty.
That's a great way to put it.
Which brings us to the core logic of the t-test.
Huh.
Because the ultimate question we are always asking in research is basically about signal versus noise.
That is the perfect way to frame it. Signal versus noise.
So let's put ourselves in the shoes of a researcher. If you are looking at that data output right now, you might be wondering, why do we even need a complex mathematical test in the first place?
Right. Why not just look at the numbers?
Yeah. Like if I have two groups of people, let's say one group studies for an exam using flashcards, and another group just rereads the textbook.
A classic psychology experiment.
Right. And I give them a memory test. The flashcard group gets an average score of 80. The rereading group gets an average score of 70.
Okay, so you have your two means.
I look at those two means.
Yeah.
80 is obviously higher than 70. Case closed, right? Why can't I just, eyeball the difference and declare flashcards the winner?
I know, it is incredibly tempting to just eyeball the averages, but a mean by itself is practically useless if you don't know the variability of the data surrounding it.
See, this is where people get tripped up. Let me make sure I actually understand this. If the average score is 75, but the data is wildly scattered everywhere, from a score of 0 to a score of 100.
Then that 75 is a terrible representation of the group. Almost nobody actually scored a 75.
Right. But if everyone in the group scored exactly 74, 75, and 76, then that 75 is an incredibly reliable representation.
Precisely. You cannot have confidence in a mean without knowing the variance.
Right.
Think about it geographically for a second.
Yeah.
If I tell you the average temperature of a city is 65 degrees, you might think, oh, it's perfectly pleasant all year round.
Sounds like San Diego.
Right. But if that city is 110 degrees in the summer and 20 degrees in the winter, the average is 65, but the actual lived experience is extreme.
Wow, yeah. The average totally hides the reality of the situation.
Exactly. In statistics, we need to know the spread. We need to know the noise.
Okay, so the spread of the data is the noise. Let's dig deeper into that, because I know there are two terms that constantly confuse everyone, including me sometimes. Standard deviation and standard error.
Oh, yes. They sound so similar.
They really do, but
Yeah.
they're measuring different things, right?
They are, and confusing them is a major stumbling block for students. So let's clarify. Standard deviation is about
Individuals.
Yes.
Yeah.
It tells you, on average, how much one single person's score differs from the group's mean. So if the mean is 80 and the standard deviation is 5, it means most individual people scored somewhere between 75 and 85.
It's the natural spread of your raw data.
Exactly. That's standard deviation.
Okay, so standard deviation is about the individual people in my study. So what on earth is standard error?
What's fascinating here is that standard error is one step more abstract. It is the standard deviation of sample means.
Wait, the standard deviation of means?
Yeah. Imagine you ran that flashcard study not just once, but 1,000 times. You grab 30 new people, test them, get a mean. Grab another 30 people, test them, get a mean.
Okay, I'm with you.
Because of random chance, you won't get the exact same mean every time. Sometimes the mean will be 82, sometimes 78, sometimes 81.
Just based on who happened to walk into the lab that day.
Exactly. If you plot all those thousands of sample means on a graph, they form their own distribution curve. The standard error tells you how spread out those means are.
Ooh.
It tells you how much your sample mean is likely to bounce around just by pure random chance.
Oh, wow. That is a massive distinction. So if I only run my study once, which is what, most researchers do, the standard error is mathematically estimating how much my one single average might be lying to me based on random sampling luck.
Exactly. Standard error is the measure of our uncertainty about the mean. It is the ultimate measure of noise in our experiment.
Which leads us perfectly to the beautiful, simple ratio at the heart of all t-tests. When you sweep away all the scary Greek symbols and the formulas,
And there are a lot of them.
there are. But the universal logic is incredibly straightforward. A t-test is simply a measure of your effect divided by a measure of your error.
Signal divided by noise. What we found divided by what we expect to happen just by chance.
I love thinking about it like tuning an old AM radio. The difference between the means, the actual effect of your flashcards or your therapy, that is the music you want to hear.
Right, the signal.
But the standard error, that natural bouncing around of the data, that is the background static. So the t-test is literally just a mathematical way of asking, how loud is the music compared to the static?
That's a brilliant way to put it. And if we connect this to the bigger picture, think about how basic division works.
Okay.
If you have a big difference between your groups, your music is loud. Let's say a difference of 20 points.
Right.
And if your standard error is very low, your static is quiet. Let's say it's just 2 points.
Let's do 20 divided by 2 is 10.
Right. You get a massive t-value of 10. A big t-value simply equals high confidence that the difference you are observing is real because the signal is 10 times louder than the noise.
Okay, I'm going to ask the listener to pause and think for a second.
Yeah.
Is the difference you are seeing large compared to the noise in the data? Because if your music is playing at a volume of 20, but your static is blasting at a volume of 40,
Then 20 divided by 40 is 0.5.
your t-value is tiny. You can't confidently claim you are hearing a song at all. You are just hearing the chaotic noise of the universe.
Exactly. And this is exactly why you can never just eyeball the difference. Two groups could look very different on paper, but if the internal variance of those groups is massive, that difference is mathematically meaningless.
The t-test basically protects us from our own pattern-seeking brains.
It forces us to prove that the signal dominates the noise.
Okay, now that we have this overarching philosophy effect divided by error, let's actually apply it. Let's start with the simplest version you can possibly run, the one-sample t-test.
Right, the one-sample t-test. It takes one single sample of data and compares its mean to a specific known population baseline.
So you use this when you aren't comparing two groups to each other, but rather comparing one group to a theoretical expectation.
Exactly.
Let's use a highly relatable example for everyone listening. You have a classroom of 10 students, and you give them a 5-question true-false quiz.
Okay, simple enough.
Now, if they haven't studied at all, and they are completely guessing, like literally just flipping a coin for every single question, we know exactly what the theoretical population mean should be.
Right. Over thousands and thousands of students flipping coins, the average score will settle perfectly at 50%.
Pure chance gives us a known baseline. 50% is our expected mean under the null hypothesis.
Wait, let's actually define that formally, the null hypothesis, because that's a term that tricks people up all the time.
Oh, absolutely. What is the null hypothesis?
The null hypothesis is the ultimate skeptical baseline. It is the assumption that absolutely nothing interesting is happening.
Nothing at all.
Right. It is the assumption that your therapy didn't work, your teaching method failed, or in this specific case, that the students are just blindly guessing. In statistics, we always start by assuming the null hypothesis is true, and the burden of proof is on our data to prove it wrong.
Guilty until proven innocent. Or rather useless until proven effective.
That's a good way to look at it.
Okay, so our null hypothesis is that the students are guessing, and their true mean should be 50. But let's say you grade the tests for your sample of 10 students, and their actual sample mean turns out to be 61%.
Okay, it's 61.
So the fundamental question you have to ask yourself is, were they just guessing and got a little lucky, or do they actually know some of the material?
This is exactly where we build our t-test. We need our measure of effect divided by our measure of error.
The effect the signal is easy. We subtract the expected null mean of 50 from our actual sample mean of 61. So our effect size is 11.
Right. Our students scored 11 percentage points higher than random chance.
Okay, so the music is playing at volume 11. But how loud is the static?
To find the static, we need the standard error of the mean. Now, without making you do the complex square roots by hand right now, let's say the data tells us the standard error for this specific set of 10 scores is 5.67.
So the data bounces around by about 5.67 points naturally.
Right, so we take our effect, 11, and divide it by our error, 5.67. That gives us a t-value of 1.94.
Okay, wait. I'm trying to put myself in the shoes of the student looking at this data on their screen. I see t equals 1.94.
Yeah.
What does that actually mean? It just looks like an arbitrary decimal. So 1.94 good? Is it bad? What does it tell us?
This raises a really important question about how we interpret the t-statistic. Let's think about the null distribution.
The null distribution, okay.
Imagine we programmed a supercomputer to simulate 10 million different classrooms of 10 students taking this exact same true-false quiz. And the computer is programmed to purely guess. It just flips digital coins.
So the computer perfectly represents the null hypothesis.
Exactly. For every single one of those 10 million classrooms, the computer calculates a t-value. Now, because it's pure chance, most of the time the classroom average is going to be exactly 50%.
Right, and 50 minus 50 is 0. So the effect is 0.
Yes, so the vast majority of the t-values the computer generates will be 0, or very close to 0. The signal is entirely dead.
But sometimes, just by dumb luck, a classroom of guessing computers will get a 60%, or maybe a 40%.
Yes. Sometimes chance gives you a slightly positive t-value. Sometimes a slightly negative t-value. And if you graph all 10 million of these chance t-values, you get a beautiful symmetrical bell curve centered exactly on 0.
Which is the null distribution.
That is the null distribution.
Yeah.
It is basically a map of what purely random noise looks like.
Okay, I get it now. So we take our real-world t-value from our actual human students, which was 1.94, and we look at where it falls on that map of random noise.
Precisely. A t-value of 1.94 means our signal was almost twice as loud as the expected noise. It is positive, so it sits off to the right side of the bell curve. Now we ask the computer, in all your millions of simulations of pure guessing, how often did you accidentally generate a t-value of 1.94 or higher?
Oh, wow. And looking at the statistical tables, the probability of getting a 1.94 or larger by pure blind luck is about 8.4%, or, as you'll see it on your output, a p-value of 0.084.
Which means, in plain English, that all of the students could have been completely guessing. It is entirely possible.
But it wasn't incredibly likely. It would only happen 8.4% of the time.
Right. It is in a gray area. But this p-value gives us a perfectly quantifiable way to express our confidence in that 61% score.
Okay, we are going to dive incredibly deep into p-values in just a moment because there is so much philosophical debate there. But first, let's expand our toolkit.
Good idea.
Because testing against a theoretical chance baseline like a coin flip is fine, but it's not what most psychologists do every day. Usually we want to know if a specific intervention actually changes human behavior over time.
Does this therapy reduce depression? Does this new drug improve focus?
Exactly. And for that, we move into the paired samples t-test. You'll also see it called the dependent samples t-test in some textbooks.
If you are designing a study, you have to ask yourself a critical question right at the start. I want you to pause and think about this. Are you comparing two separate, distinct groups of people, or are you measuring the exact same people twice?
That single distinction dictates everything about the math you will use.
It really does. If it is the same people measured twice, like a pre-test and a post-test, you must use a paired samples test.
To really grasp how this works, let's walk through an incredible piece of research. This is a 2016 study by Mayer, Song, and Spelke. They were studying infant cognition, specifically looking at whether singing to babies makes them more socially engaged.
Oh, this is a great study.
If a parent sings a specific song to an infant, will that infant naturally pay more attention to a stranger who sings that exact same familiar song?
It's a brilliant research question. It gets right at the roots of social bonding and shared culture.
So here is the methodology they used. First, parents were trained to sing a very specific new melody to their infants at home for several days. Then, the parent brings the infant into the lab for the experiment.
And they start with a baseline phase.
Right. During baseline, before the baby hears any singing from the researchers, the infant sits on the parent's knee and watches a silent video of two strangers side by side. The researchers use eye tracking to measure the proportion of time the infant spends looking at each stranger.
Establishing that baseline is critical. Why? Because every infant is totally different. Some infants might naturally prefer the stranger on the left because they have darker hair.
Or some infants might just stare at the wall because they're babies.
Exactly. You have to capture their natural, uninfluenced preference first.
Right. So after the baseline comes the intervention. Each of the two strangers in the video now sings a song to the baby. One stranger sings the familiar song the parents sang at home. The other stranger sings a totally unfamiliar song.
Then comes the crucial test phase.
Exactly. The infant watches silent videos of the two strangers again, and the researchers measure the proportion of time the infant now looks at the stranger who sang the familiar song.
This is a classic repeated measures design, because the exact same infants were measured twice, once during the silent baseline and once during the silent test phase after the singing. We can do something mathematically beautiful.
What's that?
We can look at the different scores for each individual infant.
Okay, let's make that concrete for the listener. Say, infant number 1 looked at the target stranger 44% of the time during the baseline. Just a slight natural aversion since it's under 50%.
Okay.
But after hearing the familiar song during the test phase, that infant looked at the target stranger 60% of the time.
So we literally subtract the baseline from the test phase. 60 minus 44. Infant number 1 has a positive difference score of 16%. Their attention increased by 16 points.
But infant number 4 might have looked 44% of the time at baseline, and then only 28% of the time during the test phase. They actually looked away.
They weren't a fan.
Right. So 28 minus 44 gives them a negative difference score of negative 16%.
Here is where the magic of the paired samples test comes in. It completely isolates the effect. By creating that difference score for each baby, we just subtract away the baby's individual quirks.
Oh, it's brilliant.
We don't care if a baby is a naturally long starer or a naturally short starer. All we care about is, did they change?
Now, here's where it gets really interesting. When I first learned this, it honestly blew my mind. What is the deep, dark mathematical secret of the paired samples t-test?
The secret is that the paired samples t-test is literally just a one-sample t-test in disguise. It is the exact same math.
Wait, really? So all that stuff we just did with the true-false quiz?
Yes. Once you calculate those different scores for each individual infant, you basically throw away the original baseline column of data. You throw away the test phase column of data.
You just cost them?
Yep. You are left with one single column of numbers. The differences. 16, negative 16, 5, 10, negative 2.
And then you just run a one-sample t-test on that single column of differences.
Exactly. You calculate the mean of those differences, and you test it against a null hypothesis baseline. And what is the null hypothesis for a different score? Think about it. If the singing had absolutely zero effect on the babies, what should the average difference be?
0. If nothing happened, the baseline and the test phase should be exactly the same, so the difference is 0. The null hypothesis is 0.
Exactly. You compare your mean difference to 0, divided by the standard error of those differences, and you get your t-value.
Okay, so let's look at the actual data from the study. When the researchers ran the math on just the first 5 babies, the mean difference was positive, about 5.4%.
So on average, attention went up slightly.
Right. But when they calculated the t-value, taking that 5.4 signal and dividing it by the noise of those 5 babies, the t-value is only 0.72. The signal was actually smaller than the noise.
And checking the null distribution, a t-value of 0.72 gives a p-value about 0.509.
Meaning a difference this size would happen by pure random chance about 51% of the time.
Right.
If I'm a researcher and I see p-value of 0.51, I am devastated. I would say, well, my theory is ruined. The babies didn't really care about the song. It was just random.
But you shouldn't be devastated yet, because that was only a sample of 5 infants.
Oh, yeah.
5 infants generate an enormous amount of standard error because individuals are wildly unpredictable. So what happened when they ran the test on all 32 babies in the full study?
This is the crazy part. With all 32 babies, the mean difference barely changed. It was roughly 7.3%. The raw effect size was very similar.
But
But because the sample size was much larger, the noise, the standard error, shrank massively.
this is a fundamental rule of statistics. As your sample size goes up, your standard error goes down. You are capturing a more accurate picture of the true population.
And because the noise shrank, the new t-value shot up to 2.44. The signal is now almost 2.5 times larger than the noise, and the p-value plummeted from 0.51 down to 0.020.
Which means there is only a 2% probability that an attention shift this consistent would occur by pure chance if the songs actually did nothing.
Okay, this is the perfect time to transition into the most misunderstood, fiercely debated topic in all of behavioral science.
Making decisions.
Exactly. We have our t-value. We have our p-value. How do we officially decide if our psychological manipulation actually worked? And what does that p-value actually mean? Because I know I've defined it wrong in the past.
Most people do. Let's be incredibly precise here. A p-value is the probability of obtaining your exact data, or something more extreme, by pure chance, assuming the null hypothesis is 100% true.
Assuming the null hypothesis is true. So it is the probability of the data given the null.
Yes. What students almost always get wrong is they flip it. They think the p-value is the probability that the null hypothesis is true, or they think a p-value of 0.02 means there is a 98% chance their theory is correct.
Which is completely false.
It is entirely false. The p-value only tells you how weird your data is in a world where your theory is wrong.
That is a total brain bender, but it is so important. And this leads to another major trap. Let's say I run a massive study. I get a p-value of 0.0001.
Very small.
That is highly statistically significant. So does that mean my psychological intervention is a massive world-changing breakthrough? I want you to pause and think. Does statistical significance equal practical importance?
This is perhaps the most dangerous trap in research. A small p-value does not mean your effect is massive. It does not mean it is practically important in the real world. A p-value simply means the result is highly unlikely to be random noise.
Give me an example of how that can be misleading.
Okay, let's say a pharmaceutical company invents a new pill to cure headaches. They test it against a sugar pill placebo. The placebo cures a headache in exactly 60 minutes. The new drug cures a headache in 59 minutes and 59 seconds.
So it's exactly 1 second faster.
Yes.
That is a completely useless drug. Nobody cares about 1 second when they have a headache.
Right. But if the company tests that drug on 10 million people, the standard error will shrink to almost 0. the noise disappears, and they will get a p-value of 0.00000001.
Oh, wow.
They can legally claim the drug is statistically significantly faster than a placebo. They have proven beyond a shadow of a doubt that the 1-second difference isn't a fluke of chance. It is a real, genuine 1-second difference.
But the practical significance is zero.
Exactly.
Wow. So p-values are basically a victim of sample size. If you just add more and more people to your study, eventually you will find a statistically significant difference, even if the difference is microscopic and meaningless.
Yes.
So how do we fix this? How do we measure if an effect actually matters in the real world?
This is why modern psychology journals demand that researchers report effect size alongside their p-values. The most common metric for t-tests is called Cohen's d.
Cohen's d. I see that everywhere in the literature. How does it work?
Unlike the t-statistic, which divides the signal by the standard error, Cohen's d divides the signal by the standard deviation.
Wait, so it divides the mean difference by the spread of the individuals, not the spread of the sample means.
Exactly. And why does that matter? Because standard deviation does not shrink when you add more people. The natural spread of human heights or memory scores doesn't disappear just because you measure 1 million people. It stays stable.
So Cohen's d tells you how big the effect is relative to the natural variance of human beings, regardless of how huge your sample size is.
Precisely. A Cohen's d of 0.2 is considered a small effect. 0.5 is medium. 0.8 or higher is a large effect. It basically tells you how much the two groups actually overlap.
So if you have a massive sample size, you might have a significant p-value, but a tiny Cohen's d of, like, 0.05.
And that tells you the effect is real but practically invisible in daily life.
That is such a vital distinction. Statistical significance means chance probably didn't do this. Effect size means this actually matters.
Exactly.
Now, even with all these safeguards, we still have to worry about making errors in our decisions, specifically type I errors.
Right. A type I error is a false positive. This happens when you look at your data, you get a significant p-value, and you publish a paper claiming to the world that your effect is real.
But you were wrong.
But you were wrong. It actually was just a really weird, highly unlikely fluke of random chance.
It's like rolling double sixes on dice 4 times in a row. It's rare, but it does happen. And if it happens during your experiment, you might think you've discovered magic dice.
Exactly. It's a false alarm. And we try to control for this false positive rate by setting an alpha criterion.
The famous alpha.
Yes. In psychology, the standard alpha is set at 0.05. We are basically drawing a line in the sand before the experiment begins and saying, I will only claim this effect is real if the probability of it being a chance fluke is less than 5%. We accept a 5% risk of making a type I error.
But how we draw that line on the null distribution leads to a huge philosophical choice for researchers, one-tailed versus two-tailed tests. I know students get very confused about which one to pick.
It is a profound choice. Let's look at the null distribution bell curve again. You have your 5% risk, your alpha. A one-tailed test is also called a directional test. You use this when you have a strict theory-backed hypothesis predicting the exact direction of the change.
Like in the infant study, the researchers might say, based on evolutionary biology, I am absolutely certain the infants will look longer at the familiar singer. There is no logical reason they would look less.
Right. So they take their entire 5% risk and put it all on the extreme positive tail of the bell curve.
Exactly. The bar to reach significance is a bit lower because you are only searching in one direction. But it's a gamble, isn't it?
A huge gamble, because if the infants actually looked less at the familiar singer, even if they actively hated the song and the difference was massive, the researcher would have to just ignore it. They bet everything on positive.
Which is why almost nobody uses one-tailed tests anymore, right? We generally use two-tailed tests.
Correct. A two-tailed test is non-directional. You are saying, I am looking for any difference, positive or negative. Maybe the therapy reduces anxiety, or maybe it unexpectedly increases it. I want to catch both.
But because you are looking in both directions, you have to split your 5% alpha risk in half. You put 2.5% on the extreme positive tail and 2.5% on the extreme negative tail.
And because you split that area, you have to go further out onto the edges of the distribution to hit that 2.5% mark. The critical t-value you need to reach becomes a larger number.
So a two-tailed test is mathematically more conservative. It is harder to find a significant result.
It is. It reduces your chances of making a type I error by making you prove a larger signal. That is exactly why it is the standard default in almost all statistical software.
Okay, that makes perfect sense. You want to be conservative before claiming you've discovered a new truth about human behavior. You don't want to accidentally publish a false positive.
Exactly.
We have covered so much ground here. We know how to test one sample against a chance baseline. We know how to test the same group of people measured twice using different scores. But there is one major design left. What if we have two completely different experimental conditions?
Ah, yes.
What if Group A gets a new cognitive behavioral therapy and Group B gets a standard talk therapy? Completely different people, absolutely no overlap.
This brings us to the independent samples t-test. It is designed specifically for between subjects research.
Now, before we dive into the complex math of comparing two separate groups, I have to address the elephant in the room. There is a term that haunts psychology students. It shows up on every single statistical output, usually right next to the t-value.
Degrees of freedom.
Degrees of freedom, or just DF. It sounds like a terrifying, abstract mathematical concept.
Yeah.
I think most students just ignore it entirely.
It is heavily misunderstood, but it is actually the invisible engine that makes the t-test work.
Let me try to explain degrees of freedom using an analogy that finally made it click for me, and you tell me if I have this right.
Go for it.
Imagine I tell you that I have three numbers in my head, and the mean, the average of these three numbers, is exactly 2.
Okay.
Now, how much freedom do those numbers have to be anything they want? Well, I can freely pick the first number. Let's make it 51.
All right. 50.
I can freely pick the second number. Let's make it -3. Those first two numbers were completely free to vary. But the moment I lock in those first two, the third number loses all its freedom.
Because the final mean is predetermined to be 2.
Exactly. In order for the mean of those three numbers to equal 2, that third number must be exactly -42. It is literally forced by the math.
Yep, the math dictates it.
So in a set of three numbers, only 2 of them are truly free to vary. The degrees of freedom for that set is n-1. 3 numbers minus 1 restriction equals 2 degrees of freedom.
That is a flawless visualization of the arithmetic. Every time you calculate a mean, you lose 1 degree of freedom.
But here's where I get lost. Why does this matter for a t-test? Why is it printed on my output?
Because degrees of freedom physically change the shape of the chance window, the t-distribution curve we use to find our p-value.
Wait, the null distribution changes shape. It's not just one static bell curve.
No, it is a whole family of curves. Think about the mechanics of small samples. Let's say you do a study with only 4 people. That means you only have 3 degrees of freedom.
Okay.
With only 4 people, what is the probability that you accidentally select 4 extreme weirdos, 4 total outliers?
Actually pretty high. It's easy to randomly grab 4 incredibly tall people or 4 highly anxious people.
Exactly. Small samples are wildly unpredictable. Because of that, the null distribution for 3 degrees of freedom has to account for that chaos. The curve becomes shorter and wider. It develops what statisticians call fatter tails.
Fatter tails, what does that mean for the test?
This means extreme t-values happen more frequently by pure chance because small samples lie to us more often.
So if I only have 4 people, the t-value of 2.5 might not be statistically significant because the fatter tails mean a 2.5 happens all the time by accident.
Exactly. But if you run a study with 100 people, your degrees of freedom jump to 99. What is the probability of randomly selecting 100 extreme outliers by pure chance?
Almost impossible. The average folks will drown out the weirdos.
Yes, so the t-distribution curve for 99 degrees of freedom gets narrower and taller. The tails shrink, it becomes highly accurate, closely resembling a perfect normal distribution.
So extreme t-values are incredibly rare by chance with a big sample.
Right, so you need to know your degrees of freedom so the software knows exactly which specific curve to check your t-value against to get the correct p-value.
That makes so much sense. It's basically adjusting the strictness of the test based on how trustworthy your sample size is.
That is exactly what it is doing.
Okay, armed with that knowledge, let's look at the independent samples t-test. We are comparing 2 completely separate groups, Group A and Group B. Now, because they are different people, we cannot create different scores, right? We can't pair up Bob from Group A with Sarah from Group B.
Right, that would be meaningless. They are independent. So the top half of our t formula, the signal, is just the mean of Group A minus the mean of Group B simple.
But the denominator, the standard error, the noise gets significantly more complicated.
It does, because we have 2 different groups. They each have their own variance, right?
Yeah, Group A might have scores that are tightly clustered together, while Group B might be scattered all over the place.
Yeah.
How do we figure out the total noise of the experiment? Can we just, average the two variances together?
No, and this is a crucial point. You cannot just simple average them because that creates a biased estimate, especially if your groups are different sizes.
Give me a scenario where that breaks down.
Imagine Group A has 100 participants, and they show very low variance. The data is tight. Group B only has 10 participants, and because it's a small sample, it happens to have wild, massive variance.
Okay.
If you just add the two variances and divide by 2, you are giving the crazy, unreliable 10-person group 50% of the voting power. You are artificially inflating the total noise.
Oh, I see. You're letting the small, loud group drown out the big, accurate group.
Exactly. So instead, we have to calculate what is called the pooled variance. We pool the noise together, but we weight it based on degrees of freedom. We give the variance of the 100-person group much more mathematical weight because a larger sample provides a much more trustworthy estimate of the true population noise.
Okay, I'm going to jump in right here to reassure everyone listening. If you are panicking about the algebra of weighting pooled variance, take a breath. In modern behavioral science, you will almost never have to calculate pooled variance by hand with a calculator.
No, never. Statistical software, whether it's R, SPSS, Jamovi, or whatever your lab uses, will do the heavy lifting of that massive fraction for you.
The software does the arithmetic, but you are responsible for the logic.
Right. The important part, the part you will actually be tested on in your career as a researcher, is understanding why you chose the independent test in the first place.
You chose it because your subjects are in separate, unconnected groups. You are looking at the difference between two independent means, dividing it by their mathematically pooled noise, and getting your t-value.
And once you have that t-value, the software checks it against the distribution based on your combined degrees of freedom and hands you your p-value.
There's one more incredibly useful output the software will hand you that we really need to touch on before we wrap up. Confidence intervals. Sometimes I see papers rely on these just as much, if not more, than p-values.
Many statisticians vastly prefer confidence intervals over p-values. A p-value is just a binary decision. Reject the null or fail to reject the null. It just says something happened.
Right. But a confidence interval gives you a range of plausible values for the actual population mean difference.
Exactly. So instead of just saying flashcards are better than reading, p is less than 0.05.
A 95% confidence interval might say, we are 95% confident that the true population difference between flashcards and reading is somewhere between 4 points and 12 points.
Exactly. It gives you boundaries of estimation. And it ties directly back to the null hypothesis. If your 95% confidence interval is between a +4 and a +12, notice what number is not in that range.
0.
0 is not in the interval. Because 0, the null hypothesis of no difference, is not a plausible value, you know your t-test is going to be statistically significant.
Oh, that's a great shortcut.
But if your interval was between -2 and +6, 0 is in that range. The true difference might be 0. It might be nothing. Therefore, your p-value would not be significant.
Confidence intervals give you the significance test and the effect estimation all in one intuitive package.
They really do. They're incredibly useful.
That is so practical. Well, we have covered a massive amount of statistical philosophy today. Let's do a comprehensive recap of the absolute must-know takeaways from this deep dive.
Sounds good.
First, we explored what a t-test is and why we use it. We cannot trust our eyes to just compare averages because means are meaningless without knowing the variability around them.
Second, the core logic for all t-tests is identical. Effect divided by error. Signal divided by noise. It is the mathematical ratio of the difference you observed divided by the difference you expect to see purely by random sampling chance.
Third, we have 3 main tools for different designs. The one-sample t-test compares a single group to a known theoretical baseline, like pure guessing. The paired samples test compares the exact same people measured twice, using different scores to eliminate individual noise.
And the independent samples test compares 2 completely separate groups, requiring us to mathematically pool their variance together.
Fourth, the reality of p-values. A p-value is the probability of your data occurring under the null distribution of no differences. It is not a measure of how important your finding is. To know if a finding matters in the real world, you must look at effect size, like Cohen's d.
Absolutely essential distinction.
And finally, as you tackle your data, we want to remind you that t-tests are not just rigid math procedures designed to torture undergraduates. They are incredible philosophical tools. They are tools for asking whether an observed shift in human behavior is meaningful relative to the chaotic, messy variability of the natural world.
I couldn't agree more.
Statistics is fundamentally about learning how to reason with data. It is not about being naturally good at math. If you can understand the concept of a signal cutting through static on a radio, you can understand statistics.
Well said. Before we wrap up, I want to leave you with one final provocative thought inspired by the data simulation concepts we discussed earlier.
Oh, I like a provocative thought. What is it?
Imagine a real-world scenario. Researchers use software to simulate 1,000 experiments where a true, genuine psychological effect existed. Let's say it was a drug that truly, objectively reduced depression.
Okay, a real cure.
Right. When they ran the simulation with a sample size of only 10 subjects, the standard error was so loud that the p-value almost never reached significance. They completely missed the discovery almost 80% of the time.
Wait, they had the cure, but the math told them it was useless because the sample was too small.
Exactly. But when they bumped the sample size to 100 subjects, the standard error shrank, the signal cut through the noise, and they found the true effect almost every single time.
Wow, that is actually haunting.
It really is. So
Yeah.
I want you, the listener, to mull this over as you go into the lab. How many true, groundbreaking psychological effects, cures, interventions, educational breakthroughs are hiding in the archives right now, abandoned and completely undiscovered, simply because researchers in the past didn't use a large enough sample size to hear the signal through the noise?